Hello everyone, my name is Ankit Bhardwaj and I am a research fellow at Wadhwani AI, and I'll be presenting our work on behalf of all my collaborators. Discussing the goal of the project. The overall objective was to design lockdown strategies against COVID-19 epidemic. And while designing lockdown strategies, it is important that we consider two different aspects of lockdown, which are the health aspect as well as the economic aspect. The different stakeholders would want us to focus on individual aspects, and we want to create a situation where we balance both of these aspects and create the best possible lockdown. So that's the overall goal. The approach that we take for this is to first of all create three things, which is a disease model, which models the epidemic, the intervention model that will model the lockdown, and finally the objective functions that will describe the success or failure of our lockdowns. The steps that will follow is first of all create an MDP formulation or a Markov decision process formulation. Then we'll fit the model that we have with the real world data. And followed by that, we do reinforcement learning while keeping in mind robustness and multi-objective to obtain the best possible plan for lockdown. So let's move on to the first part, which is the epidemic model. For our disease model, we are considering the SEIR class of models, which is a type of compartmental model. We divide the population into compartments which are homogeneous, and we have differential equations describing the evolution of different compartments. The model that we are using is called SEIRD. There's a small variation with SEIR that now we have a deceased compartment right here. And another change that we've made to this model is that we are using discrete time equations for evolution. And these are not differential equations. We have converted the differential equations into this discrete time step. And for intervention model or the lockdown model, what we are considering in this epidemic model is that any intervention or lockdown basically reduces the R naught or increases the transmission time. This is something that we consider for general and in general. And the lockdown, when we try to model a lockdown, we provide the following parameters which describe a lockdown. First of all is A, which basically means that which type of lockdown you want to implement. The second is the effectiveness or E of the lockdown. So different strategies for lockdowns represent different strictness levels, and that is represented by A. Then each different lockdown will have their own effectiveness on the health side of things or on increasing the transmission time. And for every lockdown, we'll have the corresponding L of A cost associated per day. And every lockdown is supposed to have a minimum duration D, which basically makes things more implementable. And the way transmission time is dependent on E and A is that transmission time is basically defined by this equation, where E into C of A is the effectiveness of a corresponding lockdown, which is how you can see that different lockdowns lead to different transmission times. The objective functions that we are looking at are burden and delay. So the objective function that we're looking at for the whole model is something like a linear combination between the health component and the economic component. But in the health component, you can look at two different types of objective functions, which are burden and delay. Now, both these types of objective functions are basically derived from QALY, which is quality adjusted life year, a very prominently used health component. And burden refers to the burden on the healthcare system above a certain threshold, which is the healthcare capacity. And delay is how long you can delay the disease. If you look at the equations here, you will find that burden is described on the infected population minus lambda, which is the hospital capacity. And delay is time step into infected population. What you have to know is that you can describe burden and delay including other compartments like recovery or deaths, but for the purpose of our work and the results that we show, we are using I or infectious population bracket. And when we consider mixed objective, we basically normalize these objectives and take a linear combination of burden and delay. The MTP formulation that we would look at is the following, where we have S, A, P, and R. S refers to the state space, which basically has all the fractions of population in different compartments. A is the different possible choices for lockdowns. P here is the transition probability matrix of going from one state to another, and R is the reward that we get in the end, which is the objective function in some sense. If we look at the parameter estimation or fitting the model to real world data, what we've done is we have taken the data for city of Mumbai, and we have created reasonable parameter ranges for our search space. And followed by that, we use RMSE loss between the predicted numbers and the actual numbers for I, R, and D compartments as the measure of parameter fit. And once we have run the search with the hyperop library, we take all the parameter sets that give us RMSE loss, which is under 10% of the best loss, as likely parameters. And then we estimate the range of the parameters, the possible range of parameters from this set of likely parameters. It gives us certain measure of uncertainty in the parameters. Moving on to reinforcement learning, we design the reward signal based on the objective function. And as you can see, the reward signal for burden would be 1 when the infectious population is less than lambda and so on. And this way we describe the reward signal, and then the accumulated reward is basically an integral of the reward signal at each time step. If you look at the mixed reward signal, it is basically a normalized version, and then you have the linear combination as it was before, just like the objective function. There are 3 strategies to deal with uncertainty. We call it FRL, DRL, and ARL. In FRL, we choose the mean of the parameter range and consider that parameter set to train our RL agent. For DRL, we consider the uniform distribution of parameters, and every episode that we generate comes from a uniform distribution of the parameter set. So from sampling this uniform distribution. In ARL, we train 2 different agents. So there's a protagonist agent and an antagonist agent. And the antagonist agent basically tries to find the worst possible parameter for this policy. And if you look at the results, if you look at the robustness results, we say the measure of robustness is the performance on the worst case. And as we would expect, ARL performs the best on the worst case because that is how we have trained it. If you look at multi-objective results, you will find that as we increase the weight of a certain objective function in the W times burden plus 1 minus W times delay, as we increase the weight, you will find that the performance on burden will improve. And the policymaker can decide the value of W by looking at different performances. In conclusion, I would say that we have developed a robust method of planning lockdowns, but there will always be a trade-off between robustness and performance, as well as a trade-off between different objectives. One thing to note is that we are using homogeneous models, so the model is very fair. And the method is limited by the quality of data, the implicit bias while estimating parameters, and the complexity of disease model. The current work is focusing on building more complex epidemic models as well as more complex objective functions. We are also working on a more interpretable objective function where we optimize the health component, given that we have an estimate of the economic budget, which will make it much more interpretable to the policymakers who are not very familiar with the entire model itself. We are also working on better estimation methods for parameters and uncertainty. And in the future, we would want to do more data collection so that we can build better real world model. And we also want to estimate a reporting rate so that we can normalize the data that we are getting. So these are the challenges in the data. Also, we would want to extract some simple rules from the model so that we can come up with some guidelines. So that's all that I have. Thank you. And if you have any questions, please raise them.